I see that everybody is in now, and we'll have Haipeng Tsai, who will be leading us from EECS. And so, Haipeng, if you could introduce yourself and tell something about yourself, and then go ahead with your topic of your presentation.
Okay, yeah, thanks, Bernie. And I've been waiting here for a while. Thanks everybody for joining the session. So, and also I'm thankful for the opportunity to share with you today. So everybody can hear me, right?
Yep.
Okay.
Yeah.
Good.
And we can hear you online also.
Okay, great. So I think I can. Oh, I think I need to start sharing the screen. Would that be okay? So it says I will stop the others screen sharing.
Bernie, you need to let him have control of the screen. Austin may help.
Yeah, maybe I can just start sharing anyway.
Yeah, you can
okay.
start sharing.
Yeah. Okay.
Sharing.
Can everybody see my screen now?
Yes.
Okay.
Yes.
Okay. Thanks everybody again. So I would just take the about an hour, 15 minutes to 1 hour to talk about smartphone technology security, and I'm going to use the case of Android, and the reason will be explained very soon. I'm going to talk about the Android systems, including the whole software stack, but particularly focusing on the Android platform and the applications. And then after introducing some of the backgrounds, I'm going to introduce some of the common types of attacks and the current defense strategies. So yeah, so that's basically the roadmap I'm going to follow today. And finally, I'm going to give some takeaways from what we looked at. So right now, there are several kinds of mobile systems, as you already know, the Android system and the iOS and the Windows Phone. And earlier days, I'm not sure how prevalent there still are today, but we have BlackBerry OS. It's kind of smart, but not that smart. But currently, as you can see, it's very clearly that the Android is definitely dominating. And if you look at further years, you can see the previous one is from, this data is not quite updated. So nobody has drawn this figure because people don't feel like it's necessary to continue to follow this kind of figure because it's so obvious, because the dominance of Android is so obvious and it will continue to rise. But generally, so by average, it's like 80%, more than 80% of all the mobile devices, not just smartphones. So most of us know smartphones, but smartphone is not the only mobile device, but of course the most dominating kind of mobile device in the even the IoT landscape. But this one basically extends the previous figure to the another year, but you can see sometimes it goes a little lower, but generally is about 80% of the entire market. So other competitors like Android, like Apple's iOS and Windows Phone, they are competitors, they are valid competitors, but they're not even close to the market share of Android. So Android basically dominating the entire mobile computing platforms, not just mobile phones or any other like mobile devices, but basically entire mobile computing platforms. And one peculiar phenomenon in the Android world is, so why Android is so thriving? And one of the reasons is, of course, is because there are so many software applications that satisfy all the different kinds of user needs. So basically, I think we all know that now, when you think about something in your life, you might be thinking, do we have an app for that, right? So, but most of the time, you're going to be satisfied because there is an app out there that help you do something that you would other do maybe through other traditional ways in your daily lives. And because of that, there are so many applications. So right now, the official store of Android, that is Google Play, they deployed a default scanning tool to fed apps against any any potential like malicious applications. and that is kind of a protection. But even with that, of course, I think you want to take this maybe with a grain of salt, because this is because this statement and this kind of statistics comes from Tim Cook from Apple, because that's one of the competitors. But still, this data is almost true. I wouldn't say it's like 99%, but at least 90% of all the mobile malware actually targets Android. And part of the reason is because Android is so impactful, right? So it influences so many people. And one thing I want to mention is Android is largely written in the Java language, but it's very different from the traditional Java applications because of some of the things that I'm going to cover in a bit. And even these days, if you look at the developer forums of Android, maybe you will notice that Java doesn't seem to be the main language these days. It's right now the language is called Kotlin, but Kotlin is essentially a variant of Java, and generally is a JVM language. It runs on the Java virtual machine. So this is kind of the software stack of the Android systems. At the top layer, you have the applications. You have all kinds of applications. We are all familiar with many of these, like the contacts, the phone app. Probably we use that a lot. We also use a lot of browsers. And I'm also going to cover a little bit why that is the case. Oh, and then, but these are the things, the other three layers at the bottom may be something that you're not so familiar with for most of the common users. But we actually have the Linux kernel at the bottom, but this is of course the customized Linux kernel in order to adapt to the limited computing resources on mobile devices. But on top of that, we have some of the libraries. These are the core libraries. Many of these libraries actually you can also see even from traditional Linux operating system, like PC Linux operating systems. But there are also a particular kinds of second layer libraries. This is actually the Android runtime. So every time when you click an app like a phone, of course there's a bunch of Kotlin code is running. But who is going to interpret the code, right? So that is the Dalvik virtual machine. But these days, Android have upgraded to what we call the ART, the Android runtime. But essentially, this is the runtime that is responsible for explaining what this app is trying to do by interacting with the kernel. But also to facilitate the Android developers to write applications conveniently, Google provides this layer is pretty thin when Android was before Android was acquired by Google, but later Google actually expanded, of course, to improve the developers' productivity by providing a lot of framework APIs, SDK, to basically turn the app development into a task of like filling the blanks, because a lot of things have already been there, like boilerplate. You have a lot of templates there. You have a lot of callbacks to fill in, then you build it up very quickly. So I'm going to, the following content of this lecture will be kind of surrounding this diagram. We will first look at the platform, which is mainly the runtime, but primarily the application framework. And later we will look at the applications. So the Android platform, as I mentioned, essentially is a customized kernel, and it's an open source operating system, particularly developed for mobile devices. And this project's open source is called the Android Open Source Project, AOSP. And this effort has been led by Google all the years since 2008, when Android was acquired. And this one has a base operating system Linux, but also has the middleware, as we just have just seen from the previous slides. And this is currently the most popular. And so on the front end, you can see a lot of Java, written code, including the platform itself, but also you actually have a lot of C language in the backend, especially in these layers, the Dalvik virtual machine. And a lot of the libraries, of course, Linux kernel is written in C, as you all know, but many of the application frameworks are actually also written in C. And the reason is clear because C is much more performance in terms of performance efficiency than Java. Because Java always, you have to go through the virtual machine, even though that's not the virtual machine we use, right? That's the runtime, which is actually optimized greatly, but still that can become a barrier for performance compared to the system level kind of language like C. So that is the platform. I'm going to cover a bit more while talking about the security mechanisms in the Android ecosystem. But let's first look at what the Android application, how they are different from the traditional Java programs, right? Because we just mentioned, so Android mostly essentially is written in Java code or some of the Java variant code. But you do not see as many security issues with traditional Java programs as you see with Android apps. So why is that, right? So this kind of explain why that's the case. Because Android has very different constructs in terms of how they are built and how they are running on top of the platform. And the traditional Android applications consist of some or all of the 4 kinds of components. So it's component-based, it's also framework-based, because remember from the previous picture, you can see most of the things have already been provided. So it built on top of a lot of existing template, boilerplate kind of code. And there are 4 kinds of components. The activity components handles all the GUIs we see. This is probably the direct interface with users, but there are also some other like backend components like services. For example, if you are using a Google Map kind of application, then there is a service running in the backend to communicate with the map server to get the updated data. Or it also receive a lot of other kind of notifications from the system or from the maybe other applications that are connected with the map. Because usually, if you use an app, the most typical case is you use the app starting from maybe a restaurant app because you want to go to a restaurant and you found their address and you want to see how to get there. Then you can launch the map app from the Yelp app, for example. And there are also broadcast receivers. So this is a kind of component provided by the system for all the applications to actually to be managed by the OS. So if your phone runs low in battery, then you want to make sure that your application would not lose data when the phone suddenly ran out of battery, right? So you want to receive, oh, the battery is low. That is one kind of like system events that the application wants to be receiving in real time, so that when the system receives that kind of a system broadcast event, you will take something, you will take some steps, basically based on what your application is doing. For example, if the application is now serving some kind of search capabilities, and you got a lot of data, and you want to save the data before the phone is forcibly shut off by the low battery, right? And also some of the applications, this is actually common. Usually if your application provides some kind of data management, then you will need to use content providers. And each of these 4 kinds of components is running in a separate thread. That's how, when you are working on your GUI, for example, you search your restaurant, and your system is actually still running without being interrupted or being blocked by the other components that are running in the backend. So that's how that is happening in this way, because they are all running in different threads. So it's kind of concurrently running multiple components. Now you may be asking, so now you have different kind of components, then of course these components should not be totally isolated, from any software construction point of view. If you have all the totally isolated components, then what's the point of having all the components in one app, right? The reason you have different components there in the app then is because you want them to interact. So this is how the Android application components are communicating. They are communicating through a mechanism called intercomponent communication. This is actually very similar to one concept we are familiar with traditional operating systems, the inter-process communication, IPC. This is another kind of component communication, but not necessarily every component is running a different process, because we just mentioned it's actually running in different threads. But you know, between different threads, you can still use the IPC mechanisms to communicate. You can use shared memory, you can use a message passing, or any other things, right? So these components, they communicate actually through message passing. And this message is called intent. So that sounds like a very intuitive word, right? Basically, you tell me what you want to do. What is your intent from the sender's app, from the sender's component? What is your intent for you to actually send the intent to the target component? And generally, these components can be, the components that are communicating could be located in the same application or could be in different applications. I think I mentioned one example. If you use the Yelp to search restaurant, when you go to a new place, right? And you want to find how to get there. So in that case, you actually have the Yelp application communicates with the map, Google Map application. So how is that done? So basically, when you click, go there, that kind of, you know, whatever, like a link or a button. So you basically have that kind of intent, but your Yelp application does not have the ability built in for searching the map. So what the Yelp application is gonna do is to send. So right now you are interfacing with the GUI of the Yelp application that is actually backed by a component called Activity A, and Activity A wants to now launch the map search capabilities. Then that is done by sending an intent by invoking this API start activity. And this activity, one of the parameters of this function call is an intent object. So you're going to send this object not to the Google Map application directly. The Android system, which is actually corresponding to the second layer I just mentioned earlier, that will going to be acting as like a mediator, right? The mediator is going to mediate and deciding who is going to take this intent, who is going to handle this request. And usually if you have multiple apps, multiple map apps installed on your phone, then that causes a problem, right? So which one should take it? So then usually the Android system will actually check which other components have their ability to handle this intent. And if there are multiple feasible ones, multiple capable ones, then the Android system will actually show you a dialog. Does that sound familiar to you, right? So sometimes you have to choose which one to use. If you have two map applications, you're gonna need to choose. Of course, the system provides a very simple convenience feature allowing you to choose whether you want to choose this particular one for all the time forward, or you want to just use it only this time, right? So when the receiver component receives this, it will basically handle these contents, and boom, there's another activity coming up, right? So that's the Google Map user interface. Now you go to the other interface, and that interface is started by a callback or even handler called onCreate. So basically, the event of opening that interface is received by this another app. And this app has a component called Activity B. That is basically corresponding to the GUI of the Google Map application. And the onCreate is called to render the user interface. And that's how it starts. So I think I kind of covered this already, but yeah, so this one kind of another diagram to show how the application works. So if you have two applications, application A has two components, A and B, and application B has component C, right? And how these two applications communicate. Actually, this one I think it is not redundant compared to the previous slides, because this one actually illustrates how inter-application communication happens. So you have application A. So the user actually have some inputs. for example, I click my power on button. Maybe that's another good example. Maybe you just touch the screen, okay? You have a screen touch kind of event. And the Android system will first take the event, not the applications. The runtime will actually monitor these kind of device interactions, and will find the handler who is able to handle this. So usually this is probably handled by the system broadcast receiver, right? So maybe every application has a broadcast receiver, and when this receiver receives these system events, they are going to receive this event. And usually the application who has the current focus, like the current focus of the window, will take that event. And when the handler is found, you will further forward that event to the capable component. And that is done through an intent, because as I mentioned earlier, all the communication between components is realized through message passing using the intent object. So you will find the handler, which is usually a callback method, and all the callback boilerplate is already provided by the Android framework. Do you remember that picture? The second layer, right? Top down, from top to the bottom, the second layer is the Android framework. So the framework have the boiler kind of callback handler, but you want usually to override it to implement your application logic to handle anything specific to your application. And you have that component A to take this, then you will go from there, right? So that's one situation. The another situation is one component A, they want to do something. So like what I exemplified just now. And then that is realized by an intent being sent to the Android system, and the other components who has the ability to take that intent will take it. And maybe another application has a component that also has the ability to take that intent, and then the system will let you choose. Okay, so I think I have provided some basic backgrounds. Now let me talk about some of the security mechanisms provided by the Android systems. So generally there are two major kinds of security mechanisms. One is called the sandbox. The other one is permission mechanisms. So every application in Android actually runs as a user process in the Linux OS with a unique user ID. So for those who are familiar with the Linux systems, you should know what this means. What this means is basically a sandboxing mechanism, right? Because every user ID, so if you ever have an experience sharing with other users a same Linux workstation, you will know that you will be able to use all your things like in an isolated environment. You should not be supposed to be able to access any other user's data, right? So that's how the sandboxing mechanism is realized, because every application uses a different user ID. It basically has a different Linux user. Then on top of that, with each application, when you launch the application is going to be hosted by a separate instance of the Android runtime, the Delphic virtual machine. So right now this is called ART, but a couple of years ago it's still Delphic virtual machine. But again, that doesn't matter so much, right? This is a runtime, and and the other way to provide some kind of security is to use the permission mechanisms. So every application needs to restrict it with respect to what kind of things you can do, what kind of information you can do, you can access by specifying what kind of permissions you need. I believe most of us have this kind of experience where you first install the application, right? Especially during the installation time, you're going to be asked what kind of permissions you want to give. Sometimes the app just quits if you don't allow it to take all the permissions. Or in other words, if you disapprove some of the permissions, the application will just quit. In other cases, the app will just proceed, but then the app will run in a limited capacity, right? You provide something, but it would not provide other things until you later give the permissions. So some of the examples of permissions is, for example, whether you allow this app to access the internet, or maybe you can access the Bluetooth, whether you can send the short message text, right? So these things can be specified as the installation time, but after Android 6.0, system also allows you to change the permissions at runtime, right? So that's the newer versions of Android. And the user can also define, actually not the users, the developers will be able to define customized permissions. So this is basically illustrates what I just mentioned, right? So you have different applications. This is a browser. This is a cool app, another cool app. This is another add-on application. You can see each of them is running, being hosted by a separate instance of the Delphic virtual machine. And each one is running as a Linux process with a unique application ID. That application ID actually represents the user ID. And this is how the sandboxing working. But at the same time, okay. So at the same time, whether one component can access another component is guarded by permissions. For example, if you have this cool app, which want to invoke the capabilities of the cool add-on, then in order to do that, you need to have that kind of permission to call another app. And whether that permission is actually approved or whether that permission needed is there is going to be checked by the Android system. So the system server is going to check that. For example, if you want to access the Wi-Fi, and the system Wi-Fi manager will check whether you have that permission. If you don't have that permission, you're not going to be able to use that. This sounds to be, right, very secure, right? But actually not really, right? So there are many other security mechanisms. I'm not going to get into that given the time. So because I do want to get into some of the more specific attacks and the defenses. You have also other kinds of security mechanisms. For example, you can have provide private components. So private components can only be accessed by another application that have the same user ID as the user ID of the accessed application, right? They're very strict. And so, and also you have some kind of APIs, the system APIs, like the framework APIs, they are protected by permissions. So the permission mechanism is not only applied for a component level, but also for a particular API. So if you want to use this API, you need to have some kind of permissions, right? So these are all the different kinds of security kind of countermeasures that are already built in by the Android system. But even with these, there are still a lot of attacks that are still possible. And let's see how that happens, right? So I may not have time to go through all of them, but I do want to at least make sure that we understand some of them with sufficient understanding. So the security attacks are usually enabled by some of the vulnerabilities, either in the Android OS itself, or in the application, or maybe in the framework APIs. But now, because more and more applications, they have built-in web browsing capabilities. So I believe you and I like that a lot, right? You don't need another browser. You can just browse some of the online content right in situ, right? You can just browse the online content within your app. So that's provided by the web component. I don't think I have time to cover that, but that is called a web view. You have the component, you have the framework provide the capabilities for you to actually easily access the web application, web capabilities. And the application level vulnerabilities. And recently there are also some of the more tricky unconventional attacks. For example, people can attack through your accelerometers, or maybe some of your sensors, your camera. So those kind of hardware oriented attacks. And recently, because you use a lot of web capabilities in the app, then people can actually use that as another channel, another attack surface to launch attacks. And another major challenge, of course, is all the defenses, they keep evolving. They are not all the same. Next, I'm going to talk about a few kinds of security vulnerabilities and attacks in the Android system. The most prominent one is data leak. So we use app for our daily lives. We have the mobile banking apps. We sometimes use our apps to manage even our personal health data. So basically, you have a lot of personal data, stored in your phone, and any data leakage can cause a lot of trouble, right? So actually, a couple of years ago, I know one of our students actually got what we call the identity theft. So the reason that happened is because he has used some of the malicious app, and that malicious app is a banking app, and the student used that app, and all the banking accounts, like SSN number, and a living address, and many other things are leaked, and leaked to the hands of some malicious parties, and that's how the identity theft happens. And the student was forced to actually leave the country and drop the study. Actually, that's one of my own students. That's one of my own students. So this is very serious, right? So data leaks happens in this kind of illustration. And you have the information source. This is where in the code, you can actually collect the sensitive data, like your bank accounts. And there is also another place in your code, in your application, that has the ability to send the information out of the app. Okay, send that to another app. So this is the app you use, app X, and you have several components, X.1, .2, .3, right? This one collects the data, and that is sent through the ICC, fire one of the intents, whatever, and that intent contains the sensitive data. And the sensitive data is sent here, and that is going to leak through ICC to another application. This is more for the ones who love programming. For others, you can probably, let me go through this very quickly. I just want to illustrate how this happened exactly, okay? So this is the Android system, and this is a runtime. So you can consider this as Delphic virtual machine instance for this application for data grabber. And that's what we call the runtime environment. And when the user type something, or the user click, maybe just touch the screen, then the intent will be triggered. And the intent will be received by this application, and the onCreate callback is going to be invoked, and that will cause a GUI to pop up. And unfortunately, in the GUI, it will obtain some of the sensitive data sent here. So the intent will get, you will create a new intent, and then you will put some data called key into the intent. And then through this activity, through this new intent, you are going to send that key. Let's suppose the key contains some user private data. And that information will going to be sent to, of course, to the Android system. The system will coordinate which other component has the ability to take it, to handle this request. By the way, I didn't mention this. Usually in the intent, you need to specify what kind of action you want to launch, right? Do you want to launch the browser? Do you want to launch the map? Do you want to make a phone call? Or do you want to use some kind of sensor like accelerometers, right? So there is an action there. And the system will check which other components has the ability to take that action. So now let's see there is another application called leaker. And this leaker has one component that has the ability to handle the action that is requested by the data grabber. And when this intent is received, it will going to be handled by this event handler. And this event handler is another onCreate function. And in this function, you can see you will first get the intent, right? That's the intent you send here. And then it's going to extract the key information from this intent. But as I said, because this is a leaker, because by name, this component is malicious, is going to use this intent and send the text message to some untrustworthy party. So that's how the key is going to be leaked through the another component in another app through the short message services to some malicious party, right? This is how the data leak happens in an inter-application communication scenario. Of course, this can also happen in intra-application scenario as well. Right, so this is one kind of vulnerabilities and attacks. So let me look at the time. So maybe I can cover another kind of attacks. Then I will gonna be jumping to the defenses. Okay, so the data injection vulnerability of attack can happen when you have an application that has a component that will receive intent from outside, and if you don't have the data validation, if you don't have the input validation, and by the way, that's how usually the XXS, the cross-site scripting vulnerabilities happen most of the time because of that. You don't check the inputs. You don't check whether the inputs come from a legitimate parties or from malicious parties. If you don't do that, the malicious guys, they can actually inject. They can send an ill-crafted intent. And that could be something, including some corrupted data or including some fake data, right? So for example, if your app is a banking app and your banking app wants to receive data from your like face scanning, right? Your face identification to identify whether you are the right user. But someone can actually inject the data channel between the face scanning app and your banking app, and by injecting the intent, and they can send some fake data, and your app, will be told forcefully that okay, this is a legitimate user, and then what's gonna happen next? I think you already know that probably, right? So this is the data injection. So let me jump to, because I think I'm given 15 minutes. So I only have 10 minutes left. So I'm not going to cover the others, even though there are a lot of other exciting contents. So like the other kinds of attacks. But let me just skip all of those, okay? So let me jump to some of the defenses recently we have for counter measurements. By the way, there are a lot of other, we have to look at some of the particular kind of attacks, but generally we have these kind of dominating types of malware in the Android systems. And the most dominant one is actually Trojan malware. Actually, one of the example we just saw is actually Trojan, right? So the private data, the key is sent through short message services. Okay, so what are the different kinds of security defenses we have deployed or maybe are being deployed in the Android ecosystems? This one may be surprising to you, but actually I personally feel like this is the most effective one. So you want to develop the built-in security. That's done from the developer's perspective. Before anything bad happens, you want to do any preventive strategies, right? You can do code reviews. You don't want to hide anything. No obscurity. If you have a lot of good security reviews, you can actually prevent a lot of vulnerabilities. And by the way, if your code does not have vulnerabilities, attackers should not have opportunities, right? The reason attackers can do all those things because you leave some room for them to do the evil things. That's the vulnerabilities. If you do a lot of good reviews, you make sure your code do all kinds of input validation. You do a lot of kind of boundary checks. You do a lot of like sanity checks, right? Then you can actually avoid many of these vulnerabilities. And the second one is that you build secure drivers. You use secure media codecs, right? So recently, there are a lot of security attacks actually leveraging vulnerable like MPEG or JPEG kind of coders. And you want to develop secure versions of those kind of things, because those are actually the infrastructure level components. And you can actually have very strict access control, but believe me, access control does not solve all the problems, right? You need to actually look at the information flow that is going through in your code, right? So you need to make sure the data flow, the code is actually doing the right behavior to prevent any information flow induced vulnerabilities. And the memory protection, you can do things like running your application in a trusted execution environment, what we call the software enclaves. You can also use address space layout randomization, those kind of techniques to make your memory more secure. And of course, you have a lot of malware defenses. So one technique so we can use, and people are actually using a lot, which is one of the fundamental techniques, is called information flow analysis. Sometimes people also call it a taint analysis. And the idea is actually to do some kind of a code analysis to label wherever the code could obtain sensitive data. And we call those places taint sources. And then you actually define how those kind of taint sources could and should propagate throughout the code data flow and control flow. So for example, here you tag this code as taint source. And when this source comes here, you add this number to another number to get the sum. And then you should accordingly tag this value of A also as tainted, because the sensitive data is now included in this memory block. Because every variable is essentially the memory block in your system, right? This one should be tainted. And if you keep tracking this, then eventually you will know where the sensitive data is going out of your memory address space of the application, right? So if you keep tracking this, you can actually detect whether you have sensitive data leak. But then not only you can use this for data leak detection, taint analysis can actually be used for a lot of other kinds of security defenses. So for example, you can use taint analysis to detect buffer overflow. You can use it to detect use after free vulnerabilities. You can use it to detect whether you have double free vulnerabilities or memory leak vulnerabilities, right? This is one of the fundamental techniques from a program analysis perspective for detecting vulnerabilities. So this is how one of the particular taint analysis works. Yeah, so let me skip this. I don't have time to cover this. Another analysis is particularly designed to detect a particular kind of confused deputy attack. Because I didn't have time to cover this, maybe I should skip this. So as in the last few minutes, let me just cover two of the techniques that developed by my group at WSU for detecting malware. So one of them, actually both of them are based on machine learning, not very fancy machine learning techniques, just like very simple machine learning techniques. But the key innovation is to find what kind of features to use. I mean, that's always probably a very important problem. If you use a deep learning, you care about how you learn the representations, but that essentially is an automatic way to do the feature engineering. But if you don't use deep learning, if you use traditional machine learning, then you need to handcraft the features. So identifying what kind of features to use is the key problem here. So what we do is that we actually identified how the different code layers in an Android applications interact. The SDK, between the SDK layers and between the user code and SDK and between the third-party libraries and the SDK. So we look at all the different interactions among different code layers in the application, and we design features. The features are generally, the percentage of calls in different kinds, in different categories among these different layers. And we use those kind of features, and we train a very simple model. And then you, of course, you have the labeled malware applications, you have the labeled benign applications. And we then do the instrumentation and run the applications. We run the applications in the real device or in the emulators. And we profile the application, we obtain the execution trace. From the execution trace, you can compute all those kinds of predefined kind of features. And based on the features, we build the behavioral profile and use that to train the supervised model. And use that for multi-class classification to classify not only benign app versus malicious app, but also different kinds of different families of malware. But this kind of learning-based application now is not novel anymore. People have done this a lot. There are tremendous numbers of papers on malware detection, especially for Android. But most of them face a key challenge, which is what we call the sustainability challenge. So we are the first one basically promoting this sustainability as one another performance metric for learning-based malware detection techniques. So if you train a model, maybe with the data from 2001, and then you use it to detect malware that actually developed in later years, so then you can see the performance keeps dropping until like 4 or 5 years, it's almost useless, right? If you get the accuracy below 50%, it's actually even worse than random guess, right? If you just throw your coin, you can get 50% accuracy. Now, if you drop below 50%, this technique becomes useless. So how can we actually sustain the models to continue working into the future without frequent retraining? So maybe you're asking, why not just retrain the model with newer samples? I mean, the question is, you may not have the newer samples available. If even you have the newer samples, you're not going to be able to detect the 0 days, right? Because by the time you have the newer samples already there, that means the malicious attacks already happened. It's already too late. So you want to be able to keep the model sustaining without being retrained on the newer samples, because you want to detect the 0 days, 0-day malware, right? So we define the sustainability metric, and we come up with a new behavioral profile called the sensitive access distribution. And I think the name is very interesting. We call this the SAD profile, right? So how sad the app is. If the app is too sad, that means that the app is malicious. Otherwise, the app may not be so malicious, right? I think I don't have time to cover all the details, but basically, we come up with this technique to compute the SAD profile for the application. And then based on the SAD profile, we also use a traditional machine learning model to detect whether this app is malicious. And we found that this SAD profile is much more sustainable than existing features used by learning-based malware detection technique. So let me wrap up very quickly because I think I'm running over time a little bit. So basically I was planning to cover some of the things, including the system platforms and the application in the Android ecosystem. And I want to talk about the Android security mechanisms, mainly sandboxing and permission mechanisms. And then I cover with some examples of the vulnerabilities and attacks in the Android ecosystems and some of the security defenses right now we have. And in the end, I concluded by talking about how can we make the malware defense solutions more sustainable, because we want to be able to defend against 0 days. So you want to make it more sustainable. Okay, so I think that's all I have today. And I'm not sure whether I have some time for questions, but if we have some questions, then I will be very happy to answer some of them. Yeah. Okay, thank you again. Thank you everybody for your time attending this session.
We do have some questions, so.
Professor Sai, I was wondering, so you were basically tracing while the app was executing what like calls it made to the APIs and stuff. Was there any thought into like reverse engineering the apps and then to obtain like a function call graph ahead of time, and then using that to classify whether it's benign or malicious, perform multi-class classification?
Oh, yes, for that malware detection technique I just covered, yes, we will do some offline kind of runtime tracing in order to detect. So it's not like on the fly or real-time detection. Yeah, but we could make that real time. Yeah, that's a good question actually.
So for sustainability, you'd probably want to avoid doing online machine learning, probably stick with batch learning techniques because.
Yeah, so actually, yeah, that's another good point. So actually some people there are already a lot of papers about that, use online learning, basically, to incrementally train the model. But the question is, you still need the new samples. But the question is, if you want to be able to detect 0-day malware, you're not going to have the samples for those kind of malware, right? You don't have the samples. So of course, how long you can sustain the model, it's not going to be infinite. You still need to balance, the need for retraining and how long you can sustain with one training. So you train once, you want to be able to let it sustain as longer as possible. But again, it's not going to sustain forever, right? But you want to make that a little longer. But generally, you may not have those newer malware samples for you to retrain the model. That's really the challenge here. Yeah, but thanks for that great question. Yeah, so let's see, do we have more questions?
Other questions? Thank you for that excellent talk.
Okay.
I didn't know there was so many ways you could attack a cell phone.
Okay, thank you, Bernie.
Yeah. We look forward to your continuing involvement in the program and to other talks, probably
Of course,
next year
of course. Yeah.
at least. Okay, thank you very much. Let's give another round of
Thank you.
applause.